What is the first thing that you probably ought to notice and make note of?
Alternating series.
That's right. So this is an alternating series. And that opens up some conditions and a door to a fairly easy path to convergence. So what you need to do next is say the limit as n goes towards infinity of the nth term. So that would be this right here. And of course, we all know that ln of whatever grows eventually pretty slowly, but it does continue to grow, right? And so as n gets closer to infinity, ln of n plus 1 will get closer to infinity. Therefore, the value of that fraction would be approaching 0. Make sense? And I think we can also observe that as n goes from 1 to 2 to 3 to 4 to 5, that the overall value of the fraction will consistently decrease towards 0. So we could continue on with the other condition and say something like if a sub n is our nth term, then a sub n plus 1 is less than a sub n for really the whole interval that we are considering. So based on the fact that it's an alternating series and those two conditions are met, what could we say about the series as it currently stands? Converges, right? And that would be because of an alternating series test concept. So bless you. Bless you again. Okay, so I'd say if you got to this point, you're getting a good grasp on the alternating series test. Have any questions on the first part? All right, so then this asks you to go one step further and say, hey, if it is converging, does it converge absolutely or does it converge conditionally? Does it need the plus minus, or does it not? So let's find out. So in considering that, we're going to say, if you wanted to write this, you could. Limit as n approaches infinity of, or what am I doing? Let's not go there yet. Sorry. Sigma of n equals 1 to infinity, absolute value negative 1 to the n over ln of n plus 1 is what we're going to consider next. So then there's all kinds of things you could think here. So let's run through them, and I'll go more or less in order of how we've covered these. So the first thing is the resulting series. Of course, the resulting series is going to get rid of the alternating element. Is it a geometric series? No. That's kind of the first one we looked at. It's not geometric, okay. Could we use like the p-test? Is it like 1 over n to the p? No, it's definitely not a p-test. How about an integral test? This is where a lot of you went. So like maybe you try this. You think, all right, integral from 1 to infinity of 1 over natural log of n plus 1 dn. You start to look at this and you realize, golly, I feel like I should know what this antiderivative is, but I don't. And a little further exploration would reveal, oh man, I really don't. I don't have any idea what this is. So this integral test would not suffice. It's also not harmonic, because if it was harmonic, the integral test would have worked. We already did the alternating series thing before, and it's not an alternating series. What does that leave us with? There's only one thing. Got to compare. It's either going to be a direct comparison or a limit comparison. I personally, in my opinion, don't see a limit comparison here. I'm not sure what you would do with that. I see a comparison, like a direct comparison. Jasmine, what were you going to say?
If it's ln of like something to p, can we still use a p-test?
No, it needs to be like an n, just like the, yeah. Needs to be just like the single variable for it to be a p-test. Okay. So, comparison. I was talking with the folks back here. When I start with comparisons, the place I always start with is this right here. The reason why I always start there and think about, hey, is this going to work for me? 1 over n is the diverging series that comes the closest to converging. It's like almost there. Because if it was like 1 over n to the 1.0000001, it would converge. Right? So this is really close, but it diverges. So I would start here. So let's do a little comparing. I think you can probably see this on the calculator. Something along these lines. I would say 0 is less than 1 over n, which is less than...
Or equal to.
That can be true. I was trying to figure out if that is actually true in this case.
Oh.
Certainly, let's put it in there because it can be. So I don't think that we need that here, but anyways. So how are you supposed to know that? I think there's a couple of ways. Number one, if the graphing calculator is available, you just graph them and you watch. You're like, hey, look, 1 over n is always below this 1 over ln of n plus 1 on the interval that we care about. If you don't have the calculator active, you'd have to almost create like a little bit of a table and look for a pattern. So you'd say, hey, when n is 1, what do I get? I get 1 and 1 over ln of 2. Okay, blah, blah, blah. You know, does this work? And I don't know. Yeah, no, that barely works, doesn't it? Yeah, that first one barely works because ln of 2 is slightly less than 1, so 1 over that would be slightly more than 1. So it works for the whole interval. Anybody graph this and confirm? I'm pretty sure. Numerically it works. All right. Okay, so then once we've established this, that 1 over n is between 0 and our target series, the one we're trying to deal with, then we can actually use the convergence or divergence of 1 over n to help us. So what we can now say is sigma from n equals 1 to infinity of 1 over n diverges. And my reasoning there is p equals 1, or you could say harmonic, or you could do, this would be the least favorable, you could do an integral test to prove that sigma of 1 over n diverges, right? But any of those three would be an option for you. So, if the series that diverges is smaller than this other series, doesn't that mean that this one here has to also diverge? So, we can then conclude and say, therefore, sigma from 1 to infinity of 1 over ln of n plus 1 also diverges. Therefore, what's the answer to the big question?
Conditional.
Yeah, the original series is a conditionally converging series. So, therefore, going all the way back to the start, this series, it does converge, but it's conditional. Converges conditionally. Okay, so that's it. Good warm up. Kind of took us back through a lot of stuff. Do you have any follow-up questions? Okay, so let's do, I hope you're ready for this. Let's do our final convergence divergence test. Okay?
Final test?
Yep. The final one. It's called the ratio test. So, in keeping with the whole, like, we're cheering for the coaches, right? Remember, nth term test, mean, geometric series test, balanced, integral test, balanced, alternating series test, soccer mom, right? Conditional, absolute, skeptical teammate, skeptical coach, whatever. The ratio test. I would say the ratio test is probably the most versatile. Have you ever had a coach, those of you that have been in, theater or athletics, you had a coach of some kind, and at some point you came to the realization that very likely your coach could probably coach almost anything as long as they kind of got the basic idea of the sport down. Have you ever had like a soccer coach and they were so good at coaching soccer and they were really able to like motivate and help you understand strategy that you thought, you know what, if they just learned a little bit about basketball, they'd probably be a great basketball coach too. You know what I'm talking about? Anybody ever had a coach like that? Or maybe it's a different discipline. Maybe it's like
A math teacher.
Right, yeah, math teacher. Oh, they're such a great math teacher. They'd be a great English teacher too, or something. No, you see what I'm saying, though, right? That makes sense. I would say the ratio test is kind of like that coach, where Jake might have had a great, guitar teacher at some point, and maybe the guitar teacher was so good at getting him to see things that he'd never seen before. You'd think, you know what? I kind of wish he knew how to play drums, because if he did, he could probably teach me how to play drums great too, because he just seems like a really great coach or teacher of guitar, whatever it might be. Maybe that's how Jake is. He understands it all so well, he could teach somebody else like 5 different things because, I don't know. That's probably the case. Who knows? The ratio test is like that. Ratio test is extremely versatile, has a few limitations, but it's very versatile, and we'll use this a lot even in the coming weeks as we kind of move out of these. We'll use it in a different way. So here we go. Here are the conditions. Here's how this works. The ratio test, believe it or not, is going to use a ratio, a fraction, right? Hopefully it's not too surprising. So the conditions are, let A sub n be a series with non-zero terms. That's not a very high bar. Not too many of the series we look at have zero, like terms that are zero. And here's how the actual ratio test works. You form this ratio, and here's that ratio. The ratio is A sub n plus 1 over A sub n. So what would you say A sub n plus 1 and A sub n would be? Like, what are those things? Yeah, A sub n would be like the first term, and A sub n plus 1 would be the second one. So if A sub n was like the fifth term, A sub n plus 1 would be the... So would it be fair to say that A sub n plus 1 is like the next term? And A sub n would be like the current term? Okay, so if you form that ratio and you calculate that limit, you can see that ratio and the limit are the same in all three of these statements. So if you form the ratio and you calculate the limit and you get you get less than 1, then you get absolute convergence. So less than 1 would be things like 1/2, 2/3, 1/8, 9/11. Yeah, Nick, go ahead.
That seems very similar to the alternating series test, when you just take A sub n, take out the alternating factor.
Yeah, so it is sort of similar, because we are removing the alternating element. I agree with you. But with the alternating series test, all we're saying is that A sub n plus 1 is less than A sub n. And what this is getting at, because we're creating a ratio, is we're saying how much less? By what factor is it less? Does that make sense? So let me give you an example. So let's say we had this, we've done this before. Let's say we had this series right here. Alternating harmonic, right? So we'd identify it as an alternating series, and we would say, all right, the limit as n goes towards infinity of A sub n, you already know what that is, equals 0, right? And then you, like kind of what you're getting at, you'd say, well, the next term is always less than the previous term, right? So by creating a ratio, by saying, hey, let's take the next term and let's divide it by the previous term, not only, and we'll see in some of these other conditions later on, not only are we hoping that A sub n plus 1 is less than A sub n, for convergence's sake, we're hoping that it's less than by an appropriate factor. So let me give you an example. Like, let me put it this way. You know that with this series, you know that if you take away the plus minus, it diverges, right? Okay. So if we tried this ratio test, n plus 1 term would be 1 over n plus 1 over 1 over n. We'd get limit as n goes towards infinity. You'd copy dot flop this and get this. And what would you get? So we'd find out later on that the ratio test is actually inconclusive in this situation. Meaning, we don't know what happens yet. But we know that, based on our previous work, that series without the plus minus will diverge, right? And so if you looked at it a little differently, because again, we're talking about degree of degree of reducing, right? We know that 1 over n, each of the terms are going to decrease little by little by little. But as you know, convergence or divergence doesn't really depend on, hey, do the terms just reduce? It depends on how fast do they get closer to 0. And by forming a ratio, you can basically quantify that and say, hey, the successive difference between these two terms is like 1/2 as far as a ratio goes. Therefore, that's fast enough to get convergence. We'll do a few examples here, maybe. It'll maybe make a little bit more sense. That's a good question. Let's see here. Let's do a few examples here. I was going to do a different one, but let's do a few examples. Anyways, so let's just discuss real briefly. We'll continue at least. If you form the ratio and you compute the limit and you get something less than 1, you'll get an absolutely converging series. However, if you do the same thing, you form the ratio, you compute the limit, and you get something bigger than 1. Now, obviously, infinity fits within that category of bigger than 1, right? Then you actually get a series that diverges, and then you get this inconclusive case if you get exactly 1. Yes, ma'am?
What if it's 0 without
What if what's 0?
What if the limit equals 0 without being...
Yeah, that's less than 1. Now, we're doing the absolute value of the terms, and so we're not going to drop down into negatives. But if you do get 0 as a result, less than 1, so yeah, convergence. Yep. I put the little note off to the side here that says, if you got an nth term with a factorial in it, probably the ratio test is going to be the best tool for the job. Although the ratio test can be used on other things as well. It can be used on a lot of things. Okay. So we've done a couple of simplifications like we're about to do here. So I'd like to do number 1 with you. And this will maybe give you a good place to start. We'll do a few examples and we'll just... Class is done at 25, I think, right? Okay. So yeah, let's do number 1 together. So as you guys know, I like to try to contextualize this a little bit, and let's pretend that number 1 is really number 18 on the AP test or number 7 on some test or quiz in the future. How on earth are you supposed to know how to use the thing that you're supposed to use? So first of all, maybe you do this in your head. Maybe you do an nth term test. What does the nth term do here if you go n approaching infinity? 0, right? You could use that relative growth rates ranking thing and, hey, it's an exponential over a factorial going to 0. That means the nth term test tells us nothing. Is it geometric? Kinda. What's the one geometric element to this? 2 to the n. But then you get this factorial and you're like, that's not geometric. So that's not, overall it's not geometric, so we can't do that. Anybody feel like doing the integral test on n factorial? No, thank you. Let's not do that. It's obviously not harmonic.
That was a sick beat.
It is not a p-series. Comparison, we might be able to make some comparison work. 1 over n's not going to be the magic potion on this one. We maybe could use comparison. It would probably take some more effort than we feel like putting into it to come up with a comparison. We maybe could do that. Limit comparison, no. It's obviously not an alternating series. So we don't care about conditional or absolute. Convergence because of that. So we're left with the ratio test or comparison. And like I said, anytime you got a factorial, I feel like ratio test will be your friend. So here's how we do this. We're going to form the ratio first. The ratio is going to be, I'll show you how to shortcut this a little bit. It's the a sub n plus 1, so it's the n plus 1th term over the nth term. So the n plus 1th term would be this. 2 to the n plus 1 over n plus 1 factorial. Basically, you just replace all your n's with n plus 1. That's your n plus 1th term, divided by your nth term. What do y'all think about that? That's your ratio. So I got to be honest, if I were doing this question, and I'm hoping that sooner or later, if you were doing this question, you would not bother writing that. Instead, you would say, you know what? I've got a fraction divided by a fraction. Why don't I just copy dot flop that immediately? So I'm hoping that you'd get to this place pretty quick and say, you know, I'd rather just go 2 to the n plus 1, bless you, over n plus 1 factorial times n factorial over 2 to the n. I'd much rather do that. Does this make sense? Okay, and we want the limit on there too, so I'll put that limit as n goes towards infinity. But before I actually try to evaluate that, I need to do some pretty significant algebra with the ratio stuff going on the inside. And we've done stuff like this earlier this semester, earlier this unit really. I'll take you through this slowly. How could you break apart 2 to the n plus 1? Like, what is that really?
2 times 2 to the n.
There we go. You got it. So 2 times 2 to the n over, bless you, we got n factorial over here. We got 2 to the n here. And this is maybe the tricky one. Can anybody think of a strategic way to break down n plus 1 factorial? Jack, what do you see?
It's just n plus 1, right? It cancels. Oh, well, sorry, I'm jumping.
You're one ahead of us.
Yeah,
Yep.
but, it's just n factorial times n plus 1.
Yeah, in fact, can I write it backwards?
That works too.
Does that make sense? Basically, like what Jack is doing there, he's just taking the first term off the factorial, right? And what remains is 1 less than that factorial. So yeah, I think that's great. And why on earth would Jack or anybody else want to do that? Now you can see easy cancellation, right? So that means this and this, the same value, so those would cancel. And then, of course, 2 to the n would cancel with 2 to the n. So this allows us to clean this up quite a bit. Limit as n goes towards infinity of 2 over n plus 1. This turns in, I mean, you got to be honest, this is a way easier limit to evaluate now after you simplified. What do you get?
0.
0, okay. So what is so important about 0?
Less than 1, smaller than 1.
Smaller than 1. Therefore, our original series does what?
Absolutely.
That's right, it converges absolutely, and we're done. Therefore, this series converges absolutely.
So what do we mean by absolutely? Is that in reference to the conditionally bit?
Yeah, so since we did the absolute value, we will automatically do the absolute value with this ratio test. So that means even if it did happen to be an alternating series, the absolute value, of course, would take care of that. But this also does then mean absolute convergence. Okay. And of course, this is with the ratio test as far as what we use to come up with that. All right. So if you haven't already taken a peek at number 2, please do. Number 2 is a little more complicated, a few more things going on, but I think that it's doable. So please look at number 2. Today, we will we'll wrap up the ratio test on Monday. Here we go. Okay, guys, can I ask you a question? Why on earth would you even think about using the ratio test here? It looks complicated. Say it again.
I don't want to do the integral of it.
Yeah, integral of that is going to be a mess / impossible. I look at it and I see a combination of things. I see a polynomial and I see geometric. If you have combinations of things, the ratio test might be the way to go. That'd be where I'd probably start. So here's what it looks like. Limit as n heads towards infinity. And then I'm going to go n plus 1th term would be n plus 1 squared times 2 to the n plus 1 plus 1, which is really n plus 2, over 3 to the n plus 1. So that's my n plus 1th term. I replaced all the n's with n plus 1. Okay. So then that's divided by or copied out flapped by 3 to the n over n squared times 2 to the n plus 1. So far, so good? All right, so then we try some cancellation. Limit as n heads towards infinity. It's going to be n plus 1 squared times 2 to the n times 2 to the 2 times 3 to the n over 3 to the n times 3 to the first times n squared times 2 to the n times 2 to the first. I just wrote it out as just one ratio at this point. There are a lot of cancellations, right? So this and this, that and that. One of those with that one. I think that's it. So then, how'd you guys deal with this? Right here and right there. What'd you do? You could expand the numerator and get n squared plus 2n plus 1. That's one way you could do it. You could also just look at it sort of in your head and think about that expansion, couldn't you? And we get to the pre-calc trick. For goodness sake, right here, when you do apply this limit, don't use L'Hopital's rule. Don't. You can. Take you a couple of steps to get there. But remember all those super rigorous little conditions you got to show? Please, just use the pre-calc trick here. And I would really, to be honest with you, I'd be pleased, okay, happy, overjoyed if you just did this. All those little details, get worked out in your mind, and you're like, hey, look, the limit of that first part's just going to be 1 times 2/3 is 1. Times 2/3 is 2/3, which is less than 1, and we finish, right? Okay. So this, of course, as I said, is less than 1. Therefore, the series, the only one that we looked at, converges. Absolutely. Okay. So 2 real quick things before we go. Please listen carefully. Number 1, there is an intro video for you guys. I guess it would be for Wednesday, wouldn't it? Because we don't have class until Wednesday. Does that sound right? So there's an intro video for the next section, which we should get to next Wednesday, sometime over the next 4 days, okay? 5 days, whatever it is. Secondly, we are